Good morning. I hope you're doing well. I'm doing quite well. It's been an interesting week. There's been a lot of, I don't want to call it soul searching, but a lot of thinking about the next steps. Last week was a very, very insightful one, and I am very happy for all of the feedback that a lot of people gave me after the angle antics that we had last week. And yeah, there's a lot to think about, and I'm keen to share it all with you. I've got a couple new things, one very exciting new thing in particular, potential, but we'll get there when we get there. Just so many things. Cool, okay, so last week we noted that there are orientation issues. So when I tell Jugglebot to move to a certain position at a certain angle, I recorded that the angles that it actually moved to were not the angles that it was supposed to move to. And yeah, the question is, how do we fix this? The first thing to note is that it's probably not only the orientation that is erroneous. The only reason why I said last week that the orientation is the thing that is erroneous is because that's the only thing that I can measure right now. I can only measure currently the angle that the platform is at, but I cannot measure the position that it's at. So when I said last week that it's the orientation that's incorrect, that's erroneous, I was probably wrong, and well, probably not entirely correct, because it's quite likely that the position is also incorrect. And this is especially likely if what I suspect is the issue is in fact the issue, which is to say that the geometry of the physical actual robot is not the same as the geometry in the model, purely as a result of my way of manufacturing it, which I have an exciting note to add in a sec. So yeah, I'm very thankful for the people in the comments of the last video, of the last stream, who noted this, who said actually like maybe it's not just the orientation. I'm glad that you said that. It's very useful. And yeah, so 3 options have been presented to me from all of you, viewers, and I think that these are 3 very, very good options. The first, but they're all kind of different in their own ways. The first is to simulate the errors until they match the observed data. And I really like this option. So the idea here is that we move the platform around and collect a whole bunch of data, a lot more than I already have so far, but just do tons and tons of data of observation points, and then we can model the Stewart platform with a little bit of variance in each of the aspects that could potentially be wrong, which I will elaborate on what those are in a sec. So basically, generate a virtual Stewart platform of Jugglebot that is wrong in some small way, and then get it to move in all of the ways that we're getting the current Jugglebot to move, and see if the errors that it observes from where it should be are the same as the errors that we're getting on the actual robot. If they are the same, then that means that we've probably landed on the actual configuration of the actual real Jugglebot. I really like this idea. I think it's a very clever idea, but my biggest gripe with it is that it requires the forward kinematics of a Stewart platform, which I am very thankful that I have been able to avoid up until now. The idea, to explain why this is a problem, there's 2 types of kinematics that are kind of relevant for robotics, and I think that exist at all. One is inverse kinematics, which is what I've been doing so far, which is where I say I want, in the case of a Stewart platform, I say I want the platform to be here at this specific pose, so position and an orientation. How long do all of the legs need to be to get the platform there? That's actually fairly straightforward for a Stewart platform if you're a computer and you can do matrix math really quickly. That's very straightforward to do. There's always one solution. It's very nice, very elegant, just matrix math, done. Forward kinematics, however, is the opposite problem, where we say, I want the legs to be this long, where does the platform end up? And this is a problem for parallel mechanisms like Stewart platforms, where there's multiple things connecting the base and the end effector. And yeah, I haven't looked into this really as much as I ought to have, but what I have seen is that you often end up in situations where there can be many, many, many different solutions. So of course many of them are impossible. So for example, if you had no restrictions whatsoever on where the platform could be, if you say I want all the legs to be the exact same length, the platform could be above the base, or it could also be below the base, or it could also probably have all of the legs twisted around, so the whole thing is just like flipped almost. There are many poses that the forward kinematics will tell you are valid based on the lengths of the legs, but are in fact impossible. And without some way to filter those out, the simulation kind of falls apart. You have to be able to filter these out. I have been doing a little bit of reading into this, only just briefly, and it seems like there are now methods to do this where you can kind of set bounds of like, I'm expecting the platform to be around here, so only accept solutions that are in this kind of zone and just ignore all the other ones. Maybe that sort of thing would work, but I'm not sure. Yeah, if anyone's got any thoughts, I would love to know. But aside from that, I really like this, this path, and yeah, I've got more to say about that a little bit later. But I haven't done too much on that for now. The second option is to take really careful measurements of the actual robot and just go around and measure everything that I need to measure and try to get a good idea of where things actually are on the actual robot. But this is a little bit tricky with the tools that I own because the most precise linear measurement tool that I have are my Mitutoyo calipers, which have a range of like 200 millimeters or something like that. So not quite enough to measure the 600 mil legs. And that's about it. And I've got a bunch of rotary encoders, but nothing super, super precise. And the rotary encoders need a bit of finagling to get to measure linear distances, which we'll see soon. The third option is to accept the error and work around it. So recognize that this error is going to be here and try to change the robot so that it is less affected by these errors. For example, by having a bigger hand and by using different balls. Now, I absolutely agree on the bigger hand thing. This is the old hand. The fact that I have it off the robot suggests something, which we will see soon. But as we can see, it's fairly small. And I mentioned last week that this hand size was chosen fairly arbitrarily. So yes, I agree that this ought to change. There were a lot of people who were saying like, hey, why is the hand so small? Like, you should make that a bit bigger. Yeah, agreed. However, on the different balls point, Luke, who is a professional juggler, who I've mentioned before, had a suggestion of using hacky sack style balls. So that way, and with a larger hand. And that way, the problem that I mentioned last week of these round, very spherical kind of firm balls, like rolling around and not actually landing in the hand, that wouldn't really be a problem with hacky sack balls because they would just like hit the ramp on the side and just slide down. Like they don't have the integrity to like roll. So that wouldn't really be a problem. However, something that I haven't mentioned yet is that I really, really want Jugglebot to be able to juggle these balls for its debut video. And the reason why I want these is because they are LED balls. That was a bit out of time. Wow, that color looks so different on the camera. I'm gonna have to figure out some good way to film these. It's kind of tricky. I've tried filming myself with them, but it's really hard to get on camera, but I'm confident I can figure that out. But I think filming this will be amazing. Having a short little routine that Jugglebot can do with LED balls, I think would look incredible. So I really, really want it to be able to juggle these. I think that will have a massive like wow factor in its debut video. And these are, funnily enough, pretty much exactly the same size as the green balls. They are very similarly heavy. I can't remember exactly what the weight difference is, but very, very similar in their shape and their structure, except these are even, the LED ones are even more stiff. So they would roll even more. Yeah, so it's worth keeping that in mind with future changes that we make. So, yeah, after all of this, so the first two solutions or options are kind of, it's uncertain how precisely I would need to make both of these because I don't really know how big of an effect small errors can make. So, do small geometry errors even matter at all? Like if the legs were off by like 0.5 millimeter, does that matter? Who knows? Turns out some people do know. There is a very, very interesting paper that was suggested by Hooks, who has been a long-time contributor to the Jugglebot project. It's been, yeah, it's very cool to see Hooks still active and contributing. Very, very cool. There's a link in the description to this paper if you're interested in checking it out. One snapshot that I want to just present right now, or show you right now, is that the unexpected behavior in accuracy is mainly caused by machining and assembly errors, which is exactly the cause of the errors that I am experiencing right now, or I'm under the impression that I'm experiencing right now. So it's cool to see that this is not just a me problem. This is an actual problem with Stewart platforms, which is kind of funny because, as you can probably imagine, I did and have done a lot of reading into Stewart platforms over the last couple of years, and this has never come up. Never have I seen any references to, hey, by the way, these systems are potentially, we'll see in a sec, susceptible to errors as a result of their construction. It's kind of funny. No one really talks about this. But anyway, here we are. So this is the actual paper itself, and there's a couple of things that I want to show in this. So one, I mean, you can see the little model of a Stewart platform there, which is kind of neat. Let me make this a bit bigger. The biggest thing that I want to draw attention to right now is that they measured the position of the platform using a laser system. Why am I not changing? They used a laser system that was like next to the robot, and then they moved it around to a bunch of different positions, and as far as I can tell, they could measure down to 0.001 millimeters with their laser system. So they basically moved the platform around and took a whole bunch of measurements and then used this hybrid genetic algorithm to figure out how erroneous the different geometries are. And these different geometries, they've outlined them all here. There are 42 different things that can be wrong. And these are 7 different things for each leg. So, for example, if we look at like 36, this doesn't highlight very nicely, but 36 down to 42 is like the position of the base node in the X direction, position of the base node in the Y direction, base node in Z direction, and then the 3 platform nodes in the X, Y, Z, and then the length of the leg. And we can see here that these differences, so that all these measurements are in millimeters, these differences are very, very small. So they, for example, the very first measurement, the position of the base node for the first leg in the X direction, they assumed it was 0.2 millimeters. In fact, it was 0.223. And looking through all of these, the largest difference that I could find between their given and their identified was around 0.5 millimeter or so. I think these are all in millimeters. Yeah, they're all in millimeters, yeah. The biggest difference that I could find was around 0.5 millimeter. If that, I actually can't spot it right now. It honestly looks like 0. Yeah. Very, very small though. Very, very, very small errors. And they also showed how big of an effect this actually had. So these graphs over here are showing how far away the platform is. So these dots were moving the platform to given positions. So the blue dots are the theoretical values. The red dots are before calibration. So we can see that they were up to like 1.5 millimeters vertical. They actually showed, yeah, the maximum deviation was almost 15 millimeters. And then after calibration, the maximum deviation was 0.001 millimeters, or 0.01 millimeters rather, which is pretty damn good. So the TLDR of all this is errors in the geometry of less than 0.5 millimeter maximum error can lead to a largest of 15 millimeters for the overall platform, which is insane. That is, I would not have expected that. And I am fairly confident that I have some errors in the geometry of the platform that are larger than 0.5 millimeter. I feel pretty good about that. I think that's quite likely. So, seeing this, it feels like it's a bit of a fool's errand to try and resolve this by measuring everything precisely, because I'm not going to be able to measure everything that precisely. Yes, so very, very interesting paper. I'm very glad that Hooks suggested this. I kind of wish that I took on board the outcomes of this a little bit sooner than I did, but, and I'll explain exactly what I mean by that in a sec, or you'll see what I mean, but it's still very, very interesting, and I expect to be returning to this later. I think this is going to be very useful to calibrate Jugglebot properly. Yeah, so interesting turnout. So then the question is, before, let's ignore the fact that we are not going to be able to, let's ignore the fact that we would need extremely precise measurements to have the measure Jugglebot and have it be correct approach to work. But how precisely can we even measure the Jugglebot? We have 42 unknowns, as we went through before. I'm not sure how I would measure the node positions, but I thought that the legs should be measurable, and we should be able to see how long these are. My biggest question here is what I've been calling the base length for the legs, which is basically the length that doesn't change. So the length, for example, between the motor and the bottom of the base, that is fixed the whole time, and it never ever changes. But it's fairly likely that there will be some deviation in how long those lengths are as a result of these things being 3D printed and me hand constructing them all. So I figured that we should be able to measure that length difference between all of them, I thought. So I made this rig. I made a rig, and there's a link in the description to this video for the Onshape document for this. And actually, let me show you the real thing first. So this rig, I was so happy with it for a while, until I wasn't. The idea here is that I have a linear slider that's attached to an aluminium extrusion, which may seem familiar. And this block, I've made this so that it can screw onto the end of the leg. So the leg would sit in here, and then this can move up and down. And while this moves up and down, it's attached to an encoder. So we've got a rotary encoder down here, and as we slide this, that encoder picks up how far the slider has moved via the belt. So we've got a slider attached to a belt. The belt routes around and goes through an encoder. There's also a spring here and a little pulley system, and that's just here to keep tension on the belt, so that way the encoder never misses a step, so that the belt can't slide over the encoder gear, whatever it's called, pulley, without turning the encoder itself. Yes, so show you in a little bit more detail in the CAD. This is the slider thing. It can go up and down. The belt runs down and around through, let me get rid of me, through two pulleys down here just to route it around. Back up. It then goes through the encoder, so it goes around these two just idler pulleys, which are on, all of the pulleys are on bearings. This goes over the toothed pulley that's attached to the encoder, and then it goes up, all the way up to the top, around the top pulley, down around this pulley, and then it terminates on here. I haven't really done the termination thing, but it basically just wraps around. I mean, I can show you on the real thing. Where is it? Up here. It wraps around the outside of the block, and then just gets clamped down by a little 3D printed bracket. Yeah, so, cool. Yeah, and the reason why I've got this pulley system is so that the spring, which is attached to this block and this block here, so that way that spring doesn't need to have the entire stroke that this has, so that the spring will only need to stretch half as much as this part moves, just because I didn't want to overstretch my spring. And I was intending rather to use this in a way that would have the slider moving the entire length of the full aluminium extrusion. I'm not going to end up doing that, so this is a little bit overkill for what I've actually done, but whatever. Yeah, so my plan here, so I built this thing. In theory, this can measure linear movements very, very precisely. This encoder has 1024 ticks, pulses per revolution. So we have a very, very, very fine resolution. We should have a very fine resolution here. And as I move this up, we should be able to measure exactly how much this is moved, with the encoder. My plan for how to use this was threefold. The first step involves calibrating how many revolutions, or how many like ticks of the encoder is equal to a given linear distance. Because right now, like I know the radius of the pulley here, and I know the thickness of the belt, but as we found from the hand calibration with like the string wrapping around that spool, I really don't think I'd be able to theoretically estimate what the effective radius is that the belt is like running around that pulley. So I figured I would calibrate it by having these little blocks. So I've got two of these. One went up the top and one went a little bit lower. And I can set these blocks in here, measure with my calipers how far apart those blocks are, and then move the slider between the two blocks. And that way I can say, okay, the calipers have measured 200 millimeters apart. The slider has measured 5,000 ticks, or whatever the number is. Therefore, this is how many millimeters per tick we have. That was step one. Let's figure out how many millimeters per tick the encoder is measuring. The second step is to like zero out this system. So I will bring this down to like very, very low down the bottom, to some distance away that I know the length of. So I get some like, I don't know, like a stick that I know the exact length of, put this on the ground, put the stick up, measure how tall that stick is and say, okay, from the this stick is like 150 millimeters or whatever. That is equivalent to 5,000 ticks. So therefore, zero, the ground, absolutely flat, is like however many, 5,000 ticks up. And then I can use this, I can put this down next to each of the legs. So one at a time I can go around, attach them into here. For one thing, I can see how long they all are, just like in their lowest position. And then I could also get them to move around and see how precisely they can move to the positions that I'm trying to move them to. This was the plan. And my goal outcome from this is that I would be able to know exactly how long each of the 6 legs are and whether or not they are precisely tracking their position. But it all fell apart pretty quickly. I haven't entirely lost hope. I am curious to know if anyone has any thoughts on the resolution of this, but yeah, I'm not too sure myself. So to describe the problem, it all started when I realized that the pulley that I'm using on the encoder here doesn't have the exact same internal diameter as the external diameter of the encoder shaft. So you can see I have a little paper shim in here. And the reason for that is because as this spins, it's kind of hard to, that light is not great. It's really hard to hold this still enough. And honestly, it's a lot better now than it was before. But without that shim, the wheel was very clearly a little bit eccentric. It wasn't perfectly centered on the encoder, which is a bit of a problem because it means that the belt is traveling with a slightly different radius depending on the position that it's at, which kind of just throws everything off. But yeah, I put the shim in and I tried to get it by eye as close as I could. It's still not great though. And the reason why I know that it's great, or the way that I know that it's not great, is because we have some plots. Let me show you on here. Let me get rid of me. So this was the first set of data that I took. This was before the shim was in, and it was just the bare pulley. And yeah, so we've got a bunch. We have 4 measured distances, and then their respective number of counted steps. And we can see that, and I've just got a linear fit in here because I'm just assuming that it should, in theory, we should have a perfectly linear fit where we say, okay, we've moved 5,000 steps, that is equal to 200 millimeters. We've moved 10,000 steps, that's equal to 400 millimeters. It should be perfectly linear like that. So I've put a linear fit on here, but we can see that they're all ever so slightly off. And if we look at how far away, like if we just took this green line, our fitted line, as like gospel, and then we compared our actual measurements to that line, we can see that the measured distance at 85.4 millimeters is actually off by 0.1 millimeters. And like you can see the rest for all of them. So the maximum difference that we have here is 0.5 millimeter, which as we saw before, not good. It's not going to cut it. We need much, much more precise than that. So I did this again after putting the little paper shim in, and basically the same. Still not great, which is a bit unfortunate. I was kind of hoping that this would be better than it is, but it's not. And I don't really know why. So yeah, if you have any thoughts on how I can make this system a bit more accurate and where the inaccuracies may be coming from, I'd love to know. It could be the eccentricity of the pulley. I'm not certain though. I don't know. That's the most likely thing that I can think of. Everything else shouldn't really make a difference. Like all of these pulleys, even though they're 3D printed, that doesn't really matter because they're just kind of sitting there idly in the system. Yeah, I'm not too sure. However, yeah, as I said, all hope is not lost for this. So I still think that this could be useful, but not as useful as I was intending on it to be. But I will, yeah, I'll explain more about that shortly. I think it'll make more sense coming up after some other stuff. So yeah, how precisely can we measure? Not precisely enough with the tools that I own. However, what about if we had a motion capture system? This would make it a lot easier. And to this end, I have been looking at this company, Qualisys, makes some motion capture cameras, and they seem pretty good. They seem pretty damn good. I will put a link in the description. I don't have one in there right now, but I will put one in after the stream ends to this site, and you can have a look through yourself. They're pretty good. So for example, the A12 can go down to 0.04 millimeters, or even 0.03 millimeters for a different one. This would basically mean that I can do exactly the same thing that the paper did, where we put a bunch of these tracking dots on Jugglebot somehow. That's going to be a whole thing. But we put these tracking dots in and move it around, and then we can take those measurements extremely precisely and then basically do like the simulating errors approach. So we simulate a bunch of different geometries of the platform, maybe using this hybrid genetic algorithm if I can figure out how they've actually done that and what that actually means. But in some way, just try a bunch of geometries of the robot and see how accurately they can match the observed positions, which should be extremely precise, like 0.03 millimeters. While it's not the 0.001 millimeters that the paper used, still pretty damn good. And this is in 3D space. So the idea is that these will be all around my room, and I can move wherever I want in my room and be tracked like perfectly. That would be so good. Needless to say, this would be amazing for the purposes of Jugglebot's eyes. Like we could just make balls with trackers on them, and those balls will be tracked perfectly in like 150 FPS as well, in normal field of view. Like, yeah, this would be very cool. However, these systems are usually fairly expensive. I've never seen any mention online of how expensive these ones are. I cannot find it anywhere. But I got in contact with the Australian distributor, and just by like a stroke of luck, they will be around in where I am soon, next week. So they're actually going to come over next week, and we're going to kind of spec out the room and see what they think, which is pretty wild. But yeah, it should be cool. This probably won't happen for a little while, where I would actually like get them in place, but it's a potential, and I am extremely keen to get these. I think it would save a lot of hassle. So yeah, I'm very, very motivated to get these. So this is kind of like maybe put on the back burner all of these problems until I get this. But I'll add to that in a sec. Yeah, motion capture system would make it pretty damn good. Cool. On another note, I have found a huge source of backlash. So this is something that John pointed out after last week's stream, is that even acknowledging that there are geometry errors, those are probably repeatable errors, but there are also probably non-repeatable errors in the form of backlash and like slop in the system. And I've known for a little while that there was slop in the joints of Jugglebot, but I didn't really look super closely at them up until just recently. And I finally found where the problem actually is, and it's in a really annoying spot. So if you remember, I've actually been using these, basically the same joints as these for quite a long time. I was using them and then I changed to the magnet ones and now I'm using them again. And throughout that process, they've been like slowly refined and refined. And I thought that they were really good and I was really happy with them until I mounted them on the current platform. And it's like, oh, hang on, where did this backlash come from? Turns out it's from the platform joints, which are the only things that I can't replace because they are glued into the carbon fiber tubes. So you can see, it's kind of hard to get this on camera, but there's quite a bit of slop in and out, as well as up and down, if I move over to doing that. And this, it's really, really hard to get this on camera, and you can probably kind of see it there, but the problem is because the bearings are not perfectly well seated into the little hole that they're in the printed part. So the printed parts hole is like a little bit too big, and this allows the bearings a little bit of movement and a little bit of movement this way, which is not ideal. My thinking for fixing this is to just super glue the bearings in, but I haven't done that yet, just in case anyone has any better ideas. For full context, I can't reprint these parts. Those are epoxied into the carbon fiber tubes. They're fixed. And I don't really know any other way to do it other than gluing them in. I will have to be very careful to make sure that the bolt goes in straight. My thinking here is that I'll put the bolt in, get it all lined up, and then like take the bearing out, put glue just around the outside and really, really try to not get it on the inside, and then slide it in and just hope that that is perfectly aligned. Yep. I mean, I've already come to terms with the fact that I'm going to need to do quite a bit of calibration anyway, so I can't imagine this will affect that calibration process too much, but yeah, that's the plan. Super glue the bearings in. It's just really annoying that it's in that part, because if it was any other part, I could just reprint it and swap them out. But there we are. Yeah, so if you have any ideas for how to fix this, I'd love to know. Cool. One other thing. Next thing. As I alluded to at the start of the stream, I have enlarged the hand. How much does it help? I don't know. Let's find out. I did do one little test run just before the stream just to make sure that everything was working, but I haven't done any extended numbers of throws. I just did one throw over. So I haven't actually seen it try to do a longer session of throws. And I guess it's worth showing as well exactly how I've extended the hand out, because there are a couple different ways that it could be done. Let me show you on here. So as always, there's a link in the description for this Onshape model if you want to check it out. That was weird, it loaded. Whatever. Yeah, so this is the new hand. It is quite a bit larger than the old hand was. And the only real difference is that I have extruded this surface out of the top. So if we go to the hand model, I can show you in here. Where did it go? Why are all these sketches visible? What? Whatever. Yeah, so this whole top surface was not there before. So it was basically as though it was like this. So this was the old hand, this is the new hand. And these don't curve at all, these are just straight out. Yep. Just in case you were curious. Cool. So let's see what Jugglebot can do. Let me do this and put me back. Hello. Yep. So I've got to turn it all on. I am still using the old balls as well. So these are the green, very round, fairly stiff ones. But I do also have with me now these are the softest balls that I have, and it's probably I will pick up some hacky sack balls. It's worth trying. I don't plan on them ever being like the long-term solution though. But yeah, for now these are the most hacky sacky balls that I've got. They're fairly squishy, but not super. Like they still hold their shape quite a bit. Yeah, so we'll try the green balls first, and then we can see if this helps at all. What are we doing here? So we can start up the ROS network. Goes through its index search. And then we can home. As you can see, I still haven't automated this whole process. This happened this morning as well. This leg didn't home properly, so I can run the homing process again, but give it a bit of help, and then it works. Don't really know what's going on there. And now we can auto level, so we'll move up, take a measurement, and then tilt itself to offset that angle. And now we can try throwing. So we'll start off by moving over to its throw position, and now the hand is all on and ready to go. And let's do one throw back and forth. Same thing. It's overthrowing. But honestly, it looks like it's overthrowing by more than it did before. Whoa, that was very cool. I don't know if that came up on camera very well, but that did a very cool little roll. Yeah, it's still overthrowing. It's consistently landing like here. So even with the hand being this much larger, it's still not enough. Let's try the smaller ball, the more plush ball. That's a lot better. Okay, it's worth noting as well that this ball actually is slightly lighter. It's actually a fair bit lighter than the green balls. So I should be changing the model in here to reflect that, but I don't actually have I haven't coded that in yet. It's just hard coded. This is the weight. Yep. So it's impressive that it works at all. So let's try more throws, because that actually worked really well. Let's try 2 back and forths. Oh, just missed it. It's got a very impressive settling time. It lands, so even though it's overthrowing, the ball is landing, it's landing on the side and then rocking in really, really quickly. That's good. Let's try 3. I think this will be a record for Jugglebot. I don't think it's gotten more than like 2 or 3. Perfect. All right, let's go heaps. Let's go like 10. 10 back and forths. Oh, I wasn't counting. I don't know how many I got. Yeah, I really need to have some way to tell it, hey, stop, it's okay, you've dropped. Actually, maybe I can just like, oh, fuck. That's actually good. I want to try this one more time, and then I've got some other things to go through, but I want to try, if it drops, I want to try loading the ball back in, because that's something that I'm going to have to do when it does multiple balls. Nope. This is going to take some practice, I think. There we go. Just. Yeah, cool. Okay, nice. So the different ball definitely helps quite a bit, which is annoying because I want these balls to work. And these balls, oh, I should have tried it with that one, but it'll be the same as with the green ball. All right, so now everything's off. E-stop, dead. Cool. So I am very confident that that would not have made nearly that many throws with the old hand. So big hand is definitely an improvement for the softer balls. I'm not sure about for the bigger balls. When I did my test earlier, there was one, like when it did catch, it, as always, it like hit the rim and it really rolled around. Like it was rolling for like a good couple seconds. So if it tried to throw then, it would have just gone somewhere else. But with the softer balls, it definitely helps. The softer ball does a really good job of falling in, which, yes, is frustrating. If we could have LED soft balls, that would be ideal. Yeah, but yes. All right, so this big question is, what's next? We've gone through a lot, lots of issues, lots of problems, but there's still lots of room to go forwards. So because the geometry is going to be most easily resolved hopefully once I get a motion capture system, I'm kind of thinking of just like putting that to the side for a bit. Yeah, and not really worrying about that too much. And instead, working on two balls in one hand, but in a columns pattern where the precise positioning doesn't really matter that much. Like, the angle certainly doesn't matter because we're just throwing straight up. And the position, if it's wrong, it doesn't matter as long as it's consistently wrong. So if I'm telling it to throw like this, and in fact it's actually throwing like a bit wider than it's supposed to be doing, that doesn't really matter as long as it goes back and forth to the same spots every single time, which it should be doing, hopefully. And actually, I feel pretty good that it would. Yeah, so I'm thinking of doing that because that's a whole set of problems that I haven't worked on very much yet with respect to timing and like me loading that ball in, because that was a little bit tricky. That's definitely going to take some practice for me to like put the ball in at the right time. Yeah, so it's a whole other set of problems, and that will absolutely need to be solved at some point. So I'm thinking that while the geometry is kind of like in this limbo state waiting for the motion capture system, hopefully, I'm kind of thinking of working on that instead. Also, there are a couple other little things, mainly adding a UI to see in basically real time the angle that we've commanded the Jugglebot to be at, the platform at least, as well as the feedback of where we're actually measuring. And if I could, this was John's suggestion, to basically plot this and see in real time how close we are to the actual like expected position. And this would allow us also to kind of get an idea of how big of an issue the backlash is, because I could get Jugglebot to move to a certain pose and then I can push it around myself and see, okay, if I push it as hard as I can, how much does that actually affect the angle? And like how much slop does the system have as I kind of jiggle it around? How much does that angle change? That's going to be super useful. And yeah, so I'm thinking of getting that UI actually set up. Yeah. Before I forget, I mentioned before that I am not completely, I haven't completely lost hope in the utility of this structure, because I think it could still be useful to get an idea of how long each leg is relative to each other. So while this hasn't been super accurate for like the linear distance per steps traveled by the encoder, it is very consistent with moving to certain spots. So like when I had those blocks in, like the calibration blocks, it was very accurate. Every single time, it would be within one encoder count of where it was the last time. So I'm thinking, given that I'm going to be deconstructing the platform joints to superglue those bolts, to superglue the bearings in place, given that I'm doing that like deconstruction step, while I'm there, so to speak, I may as well check the lengths of all of the legs using this rig and just see how long they all are relative to each other. Unfortunately, because of this linear distance inaccuracy, I won't be able to say exactly like this leg is 0.5 millimeter longer than this one, or this leg is 0.2 millimeters shorter than this one. But I will be able to say this leg is 10 steps longer than this one, or 15 steps smaller than the other one. Which in and of itself is not super useful, but it will give me an idea of what I'm expecting when I do later go through this whole calibration process. So this will give me an idea of like, okay, I should expect leg 1 to be shorter than 6, to be longer than 5, to be shorter than 3, whatever it is. And that way when I go through this process of doing the calibration, this kind of gives me something to like reference against, is my thinking. I don't actually know how useful that will be though, because like the ground truth of the motion capture system will be more accurate than that anyway. So I don't know. I just don't want this to go to waste. I spent a little while building this and designing it, and it feels like, I don't know, if I don't use it, I don't know, we'll see what I do. I don't think it'll take that long to measure the legs, so I think I might do that, but anyway, yeah. As always, any thoughts? How did that just zoom in? Let me know. Cool, okay. A couple other things. One thing that I would like to mention now is that I have finally upgraded our internet to be double the speed that it was before. And I have 0 dropped frames now, and I'm actually thinking we might be able to start doing live streams in a higher video resolution and frame rate and everything, which would be pretty cool. And I would love to know if anyone's on the stream now and has, I don't know, it has been smooth, has been nice, good, hopefully. The last couple of weeks were really driving me mad with like YouTube just coming up with errors and stuff. Yeah, it seems to be fine now. I would love to know if it actually has been, because then I can start upping the resolution and the frame rate and everything, which would be pretty cool. It'd be good. Cool. One other thing, next thing. I am going on holiday at the end of August. Now, I was really hoping I've obviously known about this for a little while, but I was really hoping that I could get Jugglebot to the point where it was like video ready, like fancy stuff made here style video. It'd be good for that, and then I can go on holiday, and then when I come back, I can record the video, edit the video, put it out. I am increasingly less confident that that's going to be the case. My confidence level for that is pretty close to 0 at this point, especially because I am gone for a month, so that eats up a lot of time. Yeah, so I've got some thoughts on this. Let me go back to this. I'm unsure of if I should make an update video or not. I'm leaning towards making a video saying, hey, this is where Jugglebot's at right now. This is what it can do. This is what it can't do. This is the next step, sort of thing. And that way, and then after that, I'll go on holidays and then come back and continue with the development. I feel a little bit obliged to catch people up. I know that there are a lot of people who are interested in the project who don't have the time to watch all of these live streams, which is completely fair enough. So I'm thinking it could be a good idea to make this kind of like summary video, just like a quick couple minutes, maybe not a couple minutes, but we'll see how long it ends up being. Definitely not super detailed, definitely not intending on being like really flashy or anything. And yeah, make this, and that way, after I come back from holidays, if there are people who are now interested in the project and have now seen this video, they can kind of like hop in the live streams and it'll make a bit more sense to them. Yeah, I don't know. I'm leaning towards this because with like the motion capture system, and there's a couple other goodies that I haven't mentioned, I've alluded to a couple times, but I want to keep them as a surprise. But there's a couple things coming that will make the viewing experience for Jugglebot so much better. I am super excited for some of the things that are on their way to my house right now. It's going to be really cool. But I'm going to keep it as a surprise. So, but yeah, because this stuff is still arriving, I'm just kind of waiting for it. I'm thinking it might be worthwhile now to make this video before I leave. And then, yeah, that way everyone will be caught up. But we'll see. We'll see. There's so many things to do. There's like 15 different avenues that I can go down. They're all valid, they're all useful, but it's like, which one is the most useful right now? It's a tricky decision to make on any given day. But yeah, I'm thinking 2 balls in one hand, because that's a whole separate set of problems that will need to be solved and will be pretty cool, and it would be really nice to be on holiday being like, Jugglebot can do 2 balls in one hand. How cool is that? And I'll just kind of ignore the fact that it can only do 2 balls in one hand in a very specific circumstance when it's only flat. But ignoring all that, you can still do it. So that will be pretty cool. That'll be cool. I think I'll do that. Yep. All right. I think that's everything. As always, I feel like there's a few other things that I wanted to mention, but I can't remember them right now. But yeah, cool. I hope you found that interesting, as always. And yeah, good luck with everything you're doing. And there will be a stream next week. So we'll have 3 more streams. I'm going at the end of August, so we'll have 3 after this one. And then I'll be gone for a month. And to be honest, I'll probably not do one on the week after I'm back as well, because I don't expect to really get a huge amount done on the week after coming back from being gone for a month. But we'll see. So potentially 5 weeks off, I think. I need to check my calendar. I'll keep you updated. Yeah, cool. Till next week, have a good one. Where's my mouse?